So what we're going to do today is look at the differences between hydrogen bonds, dipole-dipole, and London dispersion forces. Because the goal is, if I give you a molecule, I want you to identify what kind of intermolecular bond would be holding it together. So, in way of review, let's talk about all the different types of bonds that are possible and compare them to each other from strongest to weakest. So, in my chart, these are the strongest, only if you want to the weakest. The strongest of all these bonds are the intramolecular bonds. They are the bonds that hold atoms together. In our analogy yesterday, they would be the bonds that hold Ruth's arms to her trunk, or her head to her trunk, or her legs to her trunk. That's pretty strong bonds. Pretty strong bonds. Intermolecular bonds are much weaker, and they hold molecules together. Hold molecules together. This would be the affection that Ruth has for Morgan. Okay, that friendly, I like you, you're a good friend type of affection. All we have to do is throw in a guy, pretty soon they're ready to fight each other. Because girls fight over guys, don't they? I don't know why, because guys are not worth fighting over at this age. All right, here we go. The strongest of all the intramolecular bonds is, well, you got three choices, two of which we have talked about in great lengths.
Staff and students, at this time we will conduct a lockdown drill. This is only a drill. Please go into lockdown at this time.
Where do we go?
Be notified when the drill is
Okay.
Go
In other words, nothing happens. I've locked the door. We're done. Let's go.
I don't think this is a game situation.
Folks.
I don't think we can learn right now.
Now I'm going to have to edit my fussing at you. You're irritating me. Stop it. All right. What are the two bonds that we've already talked about at length?
Ionic and covalent.
Ionic and covalent. Okay? Of those two, the strongest one is ionic. And those are the ones that hold metals to nonmetals. Metals to nonmetals. Maybe it's just me, but I don't see a lot of people looking at their homework. Molly's looking at her homework.
What homework?
Good.
Okay, we are driving. Okay.
All right. The next type, the next strongest, is one that we have not looked at yet. We will by the end of this chapter. It is the bonds holding metals to other metals. Guess what we will call it? Metallic. Metallic. Better take Simon's because I don't have them right now. Oh, here. Pass that back. Give it back to Simon. All right. Next up, what's the weakest of all of the intramolecular bonds? And this is between nonmetals and nonmetals. So, of these three, this guy will have the highest boiling point and melting point. And this will have the lowest boiling point and melting points. The most likely to be liquid is covalent. The most likely to be solid is ionic. Now, between inter and intra are bonds which are extremely unique. A girl's best friend is a diamond. And a diamond is made up of carbon atoms bonded to themselves in the form of a tetrahedron. Okay? Now what happens is that tetrahedron will itself be bonded to another tetrahedron. So in a way, a diamond can be thought of as being one giant molecule, or you can think of it as a bunch of little molecules all interconnected. So what is it? Is it an intermolecular bond?
No.
Yes. Is it an intramolecular bond? Yes. It is both. Network is both. But we don't deal with network a lot because examples of network are carbon-to-carbon bonds or silicon-to-silicon bonds or carbon-to-silicon bonds. Carbon and silicon can form 4 very stable bonds, so they're the only ones that can actually do this. Now we get to the intermolecular bonds, the bonds holding molecules together. The strongest of them all.
Students, this concludes our lockdown drill. Thank you for your cooperation.
Are we still in intro?
No, I just said we're in inter right now.
Wait, so it's net?
Oh, okay.
Alright.
So network is in the middle. Network.
Right. Hydrogen bonding. Then one of my favorite phrases in all the world, dipole-dipole. And then finally, London dispersion
Man, I wrote this in pen.
forces. London dispersion forces. London dispersion forces. Now, what are these? Well, we've not talked about them. That's what today is all about. That's what we're going to cover today. The first one we're going to cover is dipole. What is a dipole again?
London covalent.
Okay. A molecule that is covalent are sharing electrons. But what we find is that some nuclei are more attractive than another. So the more attractive or the most electronegative nuclei will have more electrons around it. So that if you were to look at them momentarily, it would appear as if there's a negative side and a positive side. And that's what they mean by a dipole moment. It has an unequal distribution of electrons. An unequal distribution of electrons. What results is that if you take a bunch of these little magnets and put them in a can and shake up the can, when you take the contents of the can and pour it out onto the table, what are you going to find? What have the little magnets done with each other? So you would see this great big ball of magnets. Right? Okay, that's dipole-dipole. When you have a bunch of dipoles, they will orient themselves positive to negative and stick to each other. I mean, you would have a fun time. You've done this. You would have a fun time pulling the magnets away from each other. It's not hard. In the same way, it's not hard to separate dipoles. They're rather weak. What do we call the bonds that hold these dipole molecules together? The world calls them dipole-dipole bonds. I like to call them dipole-dipole because it sounds more fun. Dipole, dipole-dipole. Dipole-dipole. It is adorable. Dipole-dipole bonds. So dipole-dipole bonds are between polar molecules. So let's have Hank Green explain.
Other main type of intermolecular forces are dipole-dipole forces. As you should recall from our lesson on polar and nonpolar molecules, a dipole is a separation of charges, like areas of partial positive and partial negative charge in a polar molecule such as water. Dipole-dipole forces occur when the partial charges in these molecules attract or repel each other. The molecules orient themselves so that the attraction is maximized and the repulsion is minimized. It's like two colleagues whose very different personalities improve each other's work, like Holmes and Watson. They're a great team even though they get on each other's nerves. For instance, partial charges occur in hydrogen bromide because the electrons are more attracted to the bromide than they are to the hydrogen. So the negative charges around the bromines are attracted to the positive charges around the hydrogens on other hydrogen bromide molecules, and that helps to hold the molecules close to each other.
All right. So you get two dipoles, they stick to each other. You get a bunch of dipoles, they'll form one big giant ball. Now, how do you compare dipole-dipole to a covalent or an ionic bond? Folks, it's like comparing, I don't know, Marie to Ryan. Ryan, how much can you lift? Yeah, how much can you bench? 245. How much can you bench? About 45. Okay, that's like somebody, okay, no, it would be even more like comparing Ryan to a 2-year-old baby. Okay? That's the difference. Dipole-dipole are babies compared to intramolecular bonds. They are only about 1% as strong as covalent or ionic. Okay, now, what about hydrogen bonding, Mr. Moreno? You forgot about hydrogen bonding. This is a wondrous time in television history. Back when I was a kid, we had really, every once in a while, we would have a superhero TV show. And they would be really, really bad. I remember Spider-Man back in the late 70s. Oh my gosh. See if you can watch it on YouTube. It was terrible. Now, The Incredible Hulk was actually pretty good, and it lasted about 4 or 5 years. But other than that, the old Flash was terrible. Superman was, well, I don't know. Lois and Clark was pretty good. This is a wondrous time. This week we had Arrow, which is Green Arrow, The Flash, Agents of S.H.I.E.L.D.,
These aren't cartoons.
Agent Carter. These aren't cartoons. Not this week, but okay. And coming up is Supergirl, and there's going to be a kind of Justice League show starring Firestorm and Captain Atom and I don't know. Walking Dead is not a superhero show.
Yes it is.
Smallville is no longer on there. What I meant to say, what I'm trying to say to you is that this is a wondrous time where superheroes are all over the place. What are superheroes? Most of them are humans, but they're enhanced. Why is he talking about superheroes? Because hydrogen bonding is the superhero of dipole-dipole. I mean, is Spider-Man a human? Yes, but not that many humans can crawl up a wall. There's something special about it. Is hydrogen bonding a dipole-dipole bond? Yes, but dipole-dipole bonds cannot do what hydrogen bonding can do.
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule. Although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion dipole attractions in magnitude. In a series of similar compounds, such as these group 4A hydrides, boiling point typically decreases with decreasing molecular mass. This reflects the smaller London dispersion forces that exist between smaller molecules.
Okay. Oops. I didn't mean to do that. Oh, no. Okay, we'll just...
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom, such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule.
Okay. So,
although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion dipole attractions in magnitude.
That's it.
In a series of similar compounds, such as these group 4A hydrides, boiling point typically decreases with decreasing molecular
mass.
mass.
Look on the periodic table and notice that tin, germanium, silicon,
this reflects the smaller
carbon
London dispersion forces that exist between smaller molecules.
Right? So they're all very similar. Carbon is the tiniest one of them, and it has the smallest boiling point. We live up here, folks. I'm sorry, we live up here. Methane boils. That means it condenses up here. That means from here on up, methane is a gas. So methane is very, very gassy. That means whatever's holding it together is very, very weak. Silicon tetrahydride, still very gassy, but a little stronger. Germanium tetrahydride, still very gassy, but a little stronger. This guy is still very much a gas, but it's a little stronger. So, what can we say? The smaller the molecule, the weaker the bond. Now, watch what happens when we take hydrogen.
Note, however, that in the series of group 6A hydrides, although the same boiling point trend is observed for the heaviest members of the series, the boiling point of water is anomalously high because more energy...
Okay, so where would you, if you're following this, look at that. It's almost following the exact same pattern. So water should be down here somewhere. Folks, we live here. If water was following the natural pattern, then water would only exist in our world as a gas. That means you would have to go to a very, very, very cold planet to find water as a liquid. But water does not exist as a gas. Well, it does. But
in the form of heat is required to break the hydrogen bonds and separate the molecules. The difference between
the only explanation for that is hydrogen bonding. These guys can't do the hydrogen bonding, but H2O can. And because of hydrogen bonding, then water exists in our planet as a liquid and not primarily as a gas.
Expected boiling point of water and its observed boiling point is due to hydrogen bonding.
So, why is hydrogen bonding so strong? Why? Let's look at their electronegativities, which can be found on the back of your periodic table. If you bond hydrogen to fluorine, hydrogen is 2.2, fluorine is 4.0. Folks, that's a difference of 1.8. That's in the ionic compound range. There are many ionic compounds that have that much difference. Wow, that means that hydrogen's one electron spends most of its time near fluorine. That makes it a super dipole. If hydrogen were to bond to oxygen, same thing. 2.2, 3.5, that's a difference of 1.3. Super dipole. And finally, to a smaller extent, hydrogen and nitrogen can bond together with a difference of 1.0. Still strong enough to give you some super dipole characteristics. Now you're wondering, who cares? Well, the thing is, you should. Because water sticks to itself very strongly. You can survive here on Earth. For example, because of hydrogen bonding, solid water is less dense than liquid water. So when you're in a pond and you're a little fishy, where do you get your food from? The top or the bottom? Bottom. The bottom is where the food cycle begins. Okay, you may not get if you're certain types of fish, you may not get your food from the bottom, but you get your food from the top, from something that gets its food from the bottom. Okay, the food cycle begins at the bottom. If water wasn't more dense than ice, then the ice would form down on the bottom, and it would freeze from the bottom up. So what would happen to the food cycle? All right, Stefan is getting ready to go to the pool. So he's going to go up to the diving board and jump off and try to come down like that, straight across. Okay? There is hydrogen bonding holding the water molecules together. So they will stick. That's what forms that film on the surface. Now his body has enough force to break the hydrogen bonds. But he's taking all that force and spreading it out so that the force of his body is spread out enough so that the hydrogen bonds can kind of fight back a little bit. Yes, that's why belly flops hurt. Now, if he was to take the whole force of his body and go straight down, will he have to break the hydrogen bonds? Yes, but it's so much force that the hydrogen bonds don't have a chance.
Call me fat.
No, I'm saying that you have a large surface area. That is also why water striders are able to spread out, right? You see like little ripples. They're able to spread, their bodies are designed in such a way that their force is spread out over their entire body so that they do not exert enough force to push through the hydrogen bonding layer.
What is this?
A water strider, they call them little Jesus bugs because,
That was like so.
oh my gosh, what does it look like? I mean, there's the wings. And,
That does not look like a water strider.
is that better?
No, that does not look like a water strider. Okay, now it looks like a
Looks
bug.
like a caterpillar shoe.
Finally, everyone look at Marie. She's extraordinary, isn't she? She would not be in existence today if it wasn't for hydrogen bonding. Why? She's mostly made up of water, okay, and hydrogen bonding allows that water to be liquid. Not only that, but what is not made up of water is made up of proteins. And proteins are amino acids. Amino acids are molecules with OHs sticking out from them. If there's an OH, hydrogen, fun, there's a possibility for hydrogen bonding. So last year in biology, they taught you that adenine always stuck to thymine. They probably didn't tell you why. Well, it's because sticking out from thymine is an OH. And sticking out on the same side on adenine is also an OH. Get two OHs close enough, and the O will stick to the H will stick to the other O, hydrogen bonding. Cytosine always stuck to guanine. Why? Because their OHs are oriented in the same direction, and they can hydrogen bond. they also taught you that adenine never stuck to cytosine.
How do you remember these?
That's how there was the
I don't know.
Could there be hydrogen bonding? Hydrogen bonding only works in small distances, close up. Adenine and cytosine can't connect because their OHs are too far away from each other. You also learned about the little molecule that would come through and unzip these things. Those molecules would be bristling with OHs. Is it called tRNA or something like that? mRNA? It was an RNA. It was bristling with OHs. So what it would do is, as it made its way, it would connect to the OHs and disconnect the other nucleotides. mRNA, tRNA, DNA, it's all connected by hydrogen bonding. Amino acids, all connected by hydrogen bonding. So, without hydrogen bonding, the miracle that is Marie, and she owes her life to a superhero example of dipole-dipole. All right, the last one is London dispersion forces. Behold my pen here. It's made of plastics. Plastics are non-polar. Imagine non-polar as being teeny tiny little papers that are the same size as magnets, but they're papers. What happens if you put the papers into the can that had the magnets in it and dump the papers on the table? The papers will just be all over the place. Why? Because papers don't connect to other papers like magnets connect to other magnets. Non-polar molecules are not attracted to other non-polar molecules. And yet, this pen is a solid. Something must be holding together these non-polar molecules. That something is called London dispersion forces.
Why is it
Why
called
aren't they called
London?
American dispersion?
Yeah, why is it called London?
Is called London dispersion forces, which are most common in London. I'm lying to you. They're named for the physicist Fritz London. These are the weakest of the intermolecular forces because they're based on the temporary clustering of electrons that takes place inside of molecules. They're most notable in noble gases like helium and neon, and nonpolar molecules like carbon dioxide or any kind of oil. And it's not that London dispersion forces are especially strong in these substances, it's just that there's nothing else holding them together, so even these tiny forces are noticeable in them. So what makes them work? Occasionally, in the course of their movements around their individual nuclei, electrons in a molecule become clustered together. The region where they cluster briefly acquires a slight negative charge, while other regions in the molecule experience a slight positive charge. Those positive and negative charges, although small, are strong enough to affect other nearby molecules. The positive side of the molecule attracts electrons on adjacent molecules, while the negative side repels any electrons that are close to it. These individual attractions are extremely weak and don't last very long because the clustering of electrons itself is short-lived, but the overall effect of this force is super important. London dispersion forces are the only thing that makes nonpolar substances like methane and even otherwise non-reactive stuff like helium stick together well enough to condense from gases into liquids. And we should all remember the lesson of London dispersion forces. Small, weak things can have important jobs too, which makes it sound like I think London is small and weak. I don't. London is awesome.
Okay. What he explained is the technical explanation that most scientists will give. Doesn't make any sense to me. So I like to think of this as nonpolar molecules playing chicken. Okay? Have you heard of how you play chicken? If you saw the movie Dirty Dancing, the two tractors, Kevin Bacon and the bad guy, they played chicken. Okay? If you live anywhere close to Warehouse Road, like I do, you know that every once in a while, in the middle of the night, somebody's playing chicken. Okay? What you do is you get on opposite sides of a nice, long, straight street. And you go at each other, expecting somebody at the last moment to chicken out and swerve out of the way. If no one chickens out, then they crash and they probably die. If they both chicken out in the same direction, they crash and probably die. Okay, this is not a game that you should be playing. But now you understand. So you have two molecules with equal distribution of electrons. The electron clouds don't like each other. They don't want to be near each other. So this guy comes over and says, hey, move your electron cloud to the other side. This molecule goes, no, heck with that. You move your electron cloud to the other side. I don't like your electrons. You move it. You move it. You move it. So they get on either side and they come at each other. Somebody is going to have to move it. So let's say this guy is the chicken. When he moves it, when he moves the electrons over, it exposes his back end here, which is now positive, because most of the electrons are not there. This guy wins the fight, but that attracts all his electrons over to the other side, and unbeknownst to each other, now they're attracted to each other. They will stick to each other. Okay?
Yeah, that's kind of creepy.
Well, London dispersion forces is kind of creepy. What you need to understand about London dispersion forces is that it's very, very, very weak. Okay? But it can get stronger with the number of electrons. Let me give you an example. Fluorine is number 9, so 2 fluorines has 18 electrons, is very gassy. The bonds holding it together are very, very weak.
Wait, I thought it had 14 electrons. It has 7 or whatever.
It has 9 electrons. It has 7 outer shell electrons.
Oh.
It has 9 electrons. Chlorine has 34 electrons. It is gassy, but it can easily liquefy. So what's happening to the bonds holding them together as compared to fluorine? Okay, to become a liquid, you're going to have to stick together. So how strong must your bonds be compared to something that is gassy, gassy, gassy? Stronger. Okay? Bromine is 35. 2 of them is 70. This is a liquidy, gassy type molecule. So what's happening to the forces holding it together compared to the others? Stronger. Finally, iodine is number 53. That's 106. It is a solid, liquidy type thing. No, it's mostly a solid, but you can easily liquefy it by adding a little bit of heat to it. So what does that mean? Like gallium, yes. Okay, so what does that mean? That means as the molecule gets bigger, the LDF gets stronger. That is why, my friends, Grant is over there playing with plastic. That's why it's a solid. Plastics are made up of strings of carbons, which are literally hundreds, if not thousands of carbons big. There's a ton of electrons in those molecules. Therefore, the LDF is strong. The bigger the molecule, the stronger the LDF. If it's a teeny tiny little molecule, it'll be really weak and more than likely gassy. Okay? I have now explained all the different types of intermolecular bonds. What can make LDF stronger? The number of electrons involved. The bigger, the stronger. Plastics is a perfect example of this.